we shall now consider another important property which is useful in system studies, particularly when you want to find out the response to an arbitrary input when you know the response to an impulse input through the medium of convolution integrals. So, we would like to know how the convolution in time domain, how it transforms itself in the S domain. Convolution in time domain. This is sometimes referred to as real convolution. This is said to be real convolution in the sense that we are carrying out this convolution in time domain, which is a real variable, not in the transform domain, which is a complex variable. So, this is real convolution. You recall that f t convolved with g of t is the definition is f of tau g of t minus tau d tau. You can also write this as f t minus tau g tau d tau. These are both are equivalent, and you take the variation of tau from minus infinity to plus infinity in a general case, and for causal functions where f t and g t are causal time functions, you take the limits, because f tau has a value only from tau equals 0 onwards, possibly f of tau as a f of t has an impulse at the origin, we take 0 minus to start with, and then when tau exceeds t, this becomes negative. Therefore, there is no point in carrying out the integration beyond t equals tau or tau equals t, and therefore, we take this as a t, then f tau g t minus tau. And to take care of possibility of an impulse in g of t at the origin, we take this as t plus. So, this is what we are having by means of the meaning of f of t convolved with g of t. Now, let us try to find out the Laplace transform of this. So, Laplace transform of f tau g t minus tau d tau 0 minus to t plus, that is what we are seeking. So, this will be 0 minus to infinity of this quantity 0 minus to infinity t plus f tau g t minus tau d tau, and this integration is carried out on tau, and the whatever results is a function of t, you multiply it by e to the power of minus s t dt. This integration is with reference to t. So, that is the definition of the Laplace transform of the convolution of the two time functions f t and g t, which are assumed to be causal. Now, I would like to do the integration first with reference to t and then go to tau later. Therefore, to do that I have also a function t plus here. So, to avoid that, what I can do is I will have e to the power of minus s t dt, because I would like to do the integration with reference to I will do the integration with reference to tau itself to start with. Tau equals 0 plus to t plus. Now, f of tau g t minus tau, suppose I introduce u t minus tau d tau, t equals 0 minus to infinity. Now, u t minus tau is going to be 0 when tau exceeds t. When tau exceeds t, u t minus tau is 0. Therefore, this integrand will become 0 when tau exceeds t. Therefore, I can, instead of having t plus, I can as well have infinity. Now that I have introduced this symbol ut minus tau here, I may as well take the limit of integration of tau from 0 to infinity. This is 0 minus, 0 minus. So, to ensure that the same integral is valid even here, same the values of the two integrals are the same, I have introduced purposely ut minus tau and took the limit as up to infinity, because the value of ut minus tau is going to be 0 for tau greater than t. The reason why I did this, because we would like to relate them to the Laplace transform integrals. Therefore, the limits must be from 0 to infinity. So, in order to have that kind of property, I have to purposely introduce this. All right, f t minus tau d tau. Now, this will be equal to zero minus to infinity. Now, I would like to interchange the limits of integration. This is originally the first integration with reference to tau, next integration with reference to t. Now, suppose I reverse the roles. So, I do the integration with reference to tau later and then do the integration with reference to t first. So, whatever you are having as constants whenever we are integrating with reference to t can be brought outside, which is f tau is 1 for example, d tau can be brought outside, and all functions which are involved with t are to be taken into account in the first integration. That will be g t minus tau u t minus tau e to the power of minus s t dt, e to the power of minus s t dt. Now, this is the Laplace transform of a function, delayed function g t delayed by tau seconds. If the Laplace transform of g of t is g of s, Laplace transform of the delayed time function t minus tau is e to the power of minus s tau times g of s. If g of t has for its Laplace transform g of s, g of t u t as the Laplace transform of g of s, g of t minus tau u t minus tau as Laplace transform g of s times e to the power of minus tau s. That is something which you already know. Therefore, we can write this as tau equals 0 minus to infinity of f tau d tau g of s times e to the power of minus s tau d tau, sorry, d tau comes from here. Now, in this g of s is a constant, therefore, g of s times tau equals 0 minus to infinity of f tau e to the power of minus s tau d tau. Oh, I am writing d tau twice here, it is not necessary. And this is indeed f of s. F of t e to the power of minus s t dt integrated from t equals 0 minus to infinity is f of s. Instead of t, we have the dummy variable tau. Therefore, this is f of s multiplied by g of s. So, the neat result that we are having here is finally that f t star g t star, the convolution of two time functions f t star g t star as the Laplace transform, the product of the two corresponding Laplace transforms. So, this is the important result. Convolution in the time domain corresponds to multiplication of the respective transforms in the frequency domain or the complex frequency domain, S domain. This is quite neat, and this is a rule which will be useful for our work, as I said, in system studies, where when we know the impulse response h of t, to find out the response for an arbitrary function of time, all we have to do is Laplace transform of the output will turn out to be the product of the Laplace transforms of the impulse response and the input function.